Hello, Assalamualaikum, and very good day to everyone. Last week we had go through the 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 last topic for this subject, which is related to the partial differential equation. So you know that partial differential equation is very difficult um, to solve. In order to solve this PDE, you need to break this down into two ODE, ordinary differential equation. So you will have ODE 1 and ODE 2. So when you already have this ODE 1 and 2 by some method, so usually we will use a method of separation of variable. Yeah? So what is separation of variable? Is when you have two variable, for example x and y, so you put one side x, one side y, and you make it equal to lambda, negative lambda. So you will have two ODE that has one with lambda and x, and the other one, the second ODE, with y and negative lambda. Okay, when you have these two ODE, you need to make a table that have three cases. So you have ODE number 1, this ODE number 2, and then you need to apply three cases of lambda. So you need to replace this lambda. Lambda is equal to 0, and then the second one is lambda equal to negative a squared, and then lambda equal to positive a squared. So you will get the answer in terms of C1 until C12 that I showed you last week. So today we will go again. When you already apply all of this, when you apply all these three cases, you will get what we call as general solution. So in the general solution, you will have a form of answer with unknown, with a lot of unknown. Okay, for example, you will have a1 plus the summation of n starting from n equal to 1, then a3n cos parabolic cos n pi a0 plus b3n sin n pi over a 0 . So in your general solution there will be this unknown. So but then for particular solution, you need to find what is the value of this unknown. So usually, in order to find this particular solution, you will use the boundary condition. Okay, sometimes when you want to apply boundary condition, you know that this thing can be compared to the Fourier series. If you still remember Fourier series, a topic that we learned before this topic is you have a node an and bn, and there is formula to find these three coefficient. I will show you later. Alright, so now we will look at boundary condition first. Okay, for example, if the problem give you the boundary condition, then it is easy for you. But what if the problem give you some kind of picture? So you need to take out the boundary condition from the picture itself. For example, this is for Laplace equation. Laplace equation. If you see the table I showed you last week, we have Laplace equation is related to surface. So surface meaning that you will have x and y. So this is this is y, this is x. So this is u, x, y. So when you see this line, this line is u, x, y, x1. So x is the variable. So this is along x axis, but at the point of x equal to 1. Okay. So we call this ux1, the boundary condition. So when you want to apply Laplace equation, you will have 4 boundary condition. This is 1, this is 2, this is 3, and this is 4. So 4 boundary condition. Okay, the first boundary condition is ux1, meaning that the variable is x, the along x-axis at point y equal to 1. Okay, we look at the second boundary condition. So delete this. This is 1, and then this is second boundary condition. So when you see this boundary condition, you see that it is, we need to have u, x, and y, right? So you see that here the boundary condition is along y-axis. So it is, when it is along y-axis, you just put y here. When it is along y-axis or x-axis, you just put the variable there. So if you see here, it is along x-axis, so you just put x here. So and then the second boundary condition here, it is along y-axis, so you just put y here. So because usually x will be the first one, the second one will be y. Okay, and then what point is x is? So x here is at point x equal to 0. X equal to 0. Okay, so 0 comma y equal to 0. Okay, but then here the question can give you x comma 1 is equal to 100. Maybe the temperature here is 100. Okay, and then the third boundary condition. Where is the third boundary condition? The third boundary condition is this one. Third boundary condition 1, boundary condition 2, boundary condition 3. So boundary condition 3, so try to guess. So it is along, you need to have u, x, y, of course, and then it is along x-axis, meaning that you will have to put x here, and then y is equal to 0. Okay, this 0 is will be given to you. And then the fourth boundary condition, the last one, is here. So BC3 is equal to you need to have x, y. So it is along what? Along y-axis. The variable is along x-axis. Y can change from 0 to 1. So you just put y there, and then x is at what point? Where is x? X is at 1. So here is 1. So x is equal to 1. Okay. So usually for Laplace problem, the problem related to Laplace or Earth surface, usually the question will give you all 3 boundary condition equal to 0, but only one boundary condition they have value. So for example, here we have the value of boundary condition, one of the boundary condition equal to 100. Okay, so if you see this, what you need to do first, okay, you already get the boundary condition, 4 boundary conditions. From the picture, you have already get 4 boundary condition. Boundary condition is like the initial condition, or we call it as BC. Okay, and then you see this is surface problem. Surface usually will be related to the Laplace equation. Okay, now Laplace equation, when you refer to the table, is equal to d squared u dx squared plus d squared u dy squared equal to 0. Okay, and then you have the boundary condition u0 y equal to 0, and then u1 comma y equal to 0, and then boundary condition the other two boundary condition, 2x0, this is on the x-axis, and then ux comma 1 equal to 100. So these two, x is along x-axis. You see we have x and x, so it is along x-axis. So where is it? So this one and this one, and then for these two is along y-axis. So along y-axis at point 0, so it's here, and then here is along y-axis but at point 1, so it's here. Okay, so x comma 0 along x-axis at point y equal to 0, along y-axis at point y equal to 0. Okay, sorry, at point x equal to 0, so it's here. So and then the second one is 1 comma y along y-axis, at point x equal to 1. Sorry, just now I make mistake. Okay, so now you already have your Laplace equation and then your boundary condition, then you are ready now to find the value. Okay, what you need to do now is by changing this using separation of variable. Separation of variable how? So d squared u dx squared plus d squared u dy squared equal to 0. So here you see that it is x squared, so you will have x double prime y plus here y double prime x equal to 0. Okay, so what you need to do now is you need to make you need to perform separation of variable. So x comma y, x double prime y equal to negative y double prime x. Okay, and then bring x to one side, and then this negative y double prime y equal to negative lambda. So when you have this, you can separate this into two ODE. So x double prime x equal to negative lambda, and negative y double prime y equal to negative lambda. Okay, bring this to one side, you will have negative lambda x double prime plus lambda x equal to 0. So this is ODE number 1. So this y double prime negative lambda y. Okay, so we have positive, negative and negative, so it become positive. So y double prime minus lambda y equal to 0. So this is ODE number 2. So when you have this, you need to apply 3 cases. Make a table. Okay, so this is ODE number 1. This is ODE number 2. ODE number 1 is x double prime plus lambda x equal to 0. This one y double prime y negative lambda y 0. Okay, then you apply these 3 cases. Lambda equal to, just replace this with 0, and then negative a squared, and then after that lambda is equal to positive a squared. So you will get, for example, your answer in this case uxy, okay, equal to, the solution for case number 1 is C1 plus C2 y C3 plus C4 x plus, this is the solution for of case number 1, and then plus solution for number 2, so a bit long this time, C5. Usually the solution for number 1 is shorter than compared to the solution of number 2 and 3. Okay, so cos AY plus C6 sine AY. So you know why they are using cos and sine, because they have the square root of R. Square root of R equal to negative. You have imaginary number when you square root the value of R. Okay. Okay. C5, and then multiply by C7 cos AX plus C8 sine AX. So when you see hyperbolic cos and sine, so this one, the value of R is without the imaginary number. Okay, so this is the solution for case number 2. So this is solution for case number 1. This is solution for case number 2. And then you have solution for case number 3. So C9 plus C9 cos AY plus C10 sine AY multiply by C11 cos AX plus C12 sine AX. So this is the solution for case number 3, where it's lambda equal to a squared, positive a squared. Solution of case number 3. Okay, so now you have a lot of unknown coefficients. So you have unknown coefficient C1, C2, C3, C4, C5, C6, C7, C8, C9, C10, C11, C12. So you have 12 unknown value. In order for you, so this is what we call as the general solution. General solution is with unknown. Okay, so now you need to find the particular solution. So we can use all this boundary condition that we find just now. So we have boundary condition number 1, which is the u 0 y equal to 0, and then our boundary condition number 2 is u1 y equal to 0. We apply the boundary condition that are related to y first. Okay, so we take the solution for case number 1 first. So we have case, and then we have apply boundary condition number 1 and boundary condition number 2. Okay, continue now. So case number 1, lambda equal to 0. Okay, we have our u. Okay, you know that u is equal to it is u sub 1 is when it is under the case 1, so x, y. Okay, because it is case number 1, we put 1 here, and then this is actually equal to this value here. So our u sub 1 xy is equal to this value here, the green box here. So c1 plus c1 plus c2y multiplied by c3 plus c4x. So now we apply the boundary condition number 1. Boundary condition number 1 is the value of x is equal to 0. So this x is equal to 0. So we have c1 plus c2y, and then our c4 multiplied by 0, we get 0. So we only have c3 here equal to 0. Okay, now we need to see who will be responsible to become 0. Okay, so this thing is we have the variable y here. So when the variable is y, meaning that the value changing from 0 until any number. So this y, they cannot be 0. c1 plus c2y, they are not responsible to become 0. So now only c3 is responsible to become 0, so that when it becomes 0, it multiplies to this value, we will get 0. So c3 is equal to 0. When c3 is equal to 0, we go back to this equation again. We make c3 0. So our new u1 is equal to c1 plus c2y. Our c3 is 0, right? So we have c4x. Okay, now we need to apply the second boundary condition. Apply boundary condition number 2. So boundary condition number 2, we already have our c1 plus c2y multiplied by c4 equal to 0. Now, like I mentioned just now, the variable is y, because the boundary condition number 2 is what is this just now? 1y equal to 0. So our variable is y. This what? So c1 plus c2y, they are not responsible to become 0. Only c4 can become 0. Now, you see here, our c3 is 0, our c4 is 0. So now, you know that your answer has no solution. u1 xy is equal to 0, so meaning that there is no solution, because when this c3 and c4 is 0, so this all multiplied by 0, we will get 0. So no solution for that. Now we continue for the case number 2. So case number 2 is our lambda must be equal to negative a squared. A is greater than 0. Okay, now for case number 2, the value is here from c5 until c8. Okay, okay, our u2 is equal to x squared x plus multiply by y2y. So we copy from the solution given to you just now, c5 cosine ay plus c6 sine ay. Okay, and then multiply by I continue here c7 cos hyperbolic cos ax plus c8 hyperbolic sine ax. So now the same process you need to repeat by applying the boundary condition. So applying boundary condition number 1, okay, what is boundary condition number 1 is 0y, u0y equal to 0. Okay, so variable is y, so don't touch y, so you just copy again. Applying boundary condition number 1, so we have c5 cosine ay plus c6 sine ay. So, and then our x is equal to 0. So our next is this x will become 0, this x will become 0. So when you apply cos ax, you will get 1. So cos, it's hyperbolic, cos and sine are the same. When you you want to find the hyperbolic cos 0 or cos 0, hyperbolic cos 0, you will get 1 1. So sine 0 is equal to 0, hyperbolic sine 0 is equal to 0. So when you apply, when you replace this x is equal to 0, you will get c7 hyperbolic cos x equal to 0 is equal to 1, but sine 0 will become 0. Okay, so now, so c7, who will be responsible to become 0? So because this is a variable, you cannot touch them, so only c7 is responsible to become 0. When c7 becomes 0, we go back to this solution here. We just remove c7 because c7 already 0. So our new u2xy is equal to c5 cosine ay plus c6 sine ay multiplied by c7 equal to 0. We only have c8 sine ax. Now apply boundary condition, the next boundary condition. Apply boundary condition number 2. The boundary condition number 2 just now is, I don't remember, 1y0 u 1y equal to 0. Okay, so our x now is equal to 1. Okay, so we have our new uxy just now is equal to this, the same, I'll just copy again, c5 cos ay plus c6 sine ay. Okay, this one they are not responsible to become 0. They are not responsible to become 0. Okay, and then we have this part here, c8 sine ax. So our x is equal to 0, equal to 1 now. Okay, so we have multiply by c8 sine hyperbolic sine. So our x is 1 8. Okay, like I mentioned previously, whenever you see any sine value and there is the value of a there, you know that when sine of anything equal to 0, you can compare it with sine and pi, because sine and pi is equal to 0. But this time we have hyperbolic sine, we cannot do that. Okay, this part cannot become 0, and then only this part can become 0. From this part we have C8 and sine A. So who will become 0 here? The hyperbolic sine A cannot become 0 because the hyperbolic sine of A, we have value for A greater than 0. So only C8 is responsible to become 0. When from the whole equation just now, okay, our C7 is 0, C8 is 0, so this whole part is 0. We multiply by this, also will become 0. So for case number 2, u squared xy is equal to 0, hence no solution. Now we only have, okay, during your exam, like I mentioned before, when you found a lot of things with no solution, you are in the correct direction. Don't worry. So the next one is case number 3. Now you know that when you already have 2 cases with no solution, the case number 3, most of the time you will have solution. So case number 3, lambda is equal to positive a squared, a is greater than 0. Okay. Okay, you know, U3, our U3 is this part here. This part here. So this is the solution for case number 3. We start from C9 until C12. Very long calculation, but it's simple. So our C3 now is equal to x3, x, y 3, okay, and then it is equal to C9 hyperbolic cos AY plus C10 hyperbolic sine AY. Why it is hyperbolic cos and sine? Because the value of r has imaginary number in it, and then multiply by starting from C9 until C12, right? So C11 cosine AX plus C12 sine AX. Okay, now apply the same method. So apply boundary condition number 1, you will get, so boundary condition 1 is this one, u0y equal to 0. Okay, u0y equal to 0. So our x is equal to 0 and our y is the variable, so cannot touch this y part. So this is y part y, this is part x. Because y is a variable, y is changing, okay, the value of y can change here, 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 here. So do not touch this part, can only touch the value with x. Okay, so cos 0, sine 0, we replace x with 0, right? So cos 0 we get 1, sine 0 we get 0. So we only have this part. Okay, so our C11, okay, so sorry, so our new U3 is equal to C9 cos AY plus C10 sine AY multiply by, because this is already become 0, we just remove it. So C11 cos AX. Now we need to find who is responsible to become 0 so that it is equal to 0. Okay, so this part we cannot touch, cannot become 0. C9 cos AY plus C10 sine AY, they are not responsible to become 0 because they are variable. Only C11 and cos AX. Okay, so cos AX we have value. Now only C11 are responsible to become 0. Then we go back to this thing. We need to remove C11 because C11 is equal to 0. So our new u3 is equal to c9 hyperbolic cos ay plus c10 hyperbolic sin ay multiply by c11 already 0, so we only have this c12 here, multiply by c12 sin ax. Okay, what to do next is applying the next boundary condition. Apply boundary condition number 2, which is the 1y equal to 0, u1y equal to 0. Okay, so here our x will become 1, y is the variable. So from here, okay, when we apply boundary condition, we know that c9 cos ay plus c10 hyperbolic sin ay, they cannot be 0. Only c12 and sin ax, they can become 0. Okay, when you see sin ax, this is the interesting part. When you see sin ax, you can make this equal to 0. Okay, so sin ax, so our x is 1 now, sin a equal to 0. Also sin and pi is equal to 0. So a is equal to n pi. So we have the value of a now. Okay, n is the variable, you know that. So for this solution, our C12 is not equal to 0. What if C12 equal to 0? So all three cases, we have no solution for them. So case there are infinite solution. When there is n here, you know that n can be 1, 2, 3, blah blah blah. So there are infinite solution for case number 3. So our new u3n is equal to c9 cos n pi. So a is n pi, right? N pi y plus c10 sine hyperbolic sine. So our a is n pi y multiply by, this is multiply, yeah. Okay, c12, we have the value of c12, and then we have, when c12 is sin ax, sin, our a is n pi x. Okay, this is the solution, the solution for all these three cases. We have this only, but still we have the unknown from c9 to c12. Okay, what to do now? Okay, when the question asks you, okay, the eigenvalue and also eigenfunction, right? I explained this before. So for case number 1, the PDE solution, boundary condition, for case number 1, okay, so case number 1, our u is u1, right? So u1 is equal to 0, and then the eigenvalue is usually lambda equal to 0, lambda equal to negative a squared, the lambda equal to positive a squared. And then eigenfunction is the solution for that. So just now for case number 1, we have no eigenvalue, no eigenfunction. So no solution, meaning that we have no eigenvalue and no eigenfunction. Done. And then, so for case number 2, when lambda equal to negative a squared, we call our u as u2 is equal to 0. Also no solution because we have no eigenvalue, so that the meaning is no eigenvalue and no eigenfunction. And then we have case number 3. This one we have solution for this. This is for lambda equal to positive a squared. So our u3, okay, we have n because the solution is we have the value of n, because we have the value of a is equal to n pi. So our u3 is a bit long. So our u3 is equal to, just now we copy a3, or you can put a3n. I just put a3 here because we know that it has n value, cos n pi y plus b3 sine n pi y multiplied by sine n pi x, where our n can be any value 1, 2, 3 ... And what is the eigen? Because it has solution, right? So it has eigenvalue and eigenfunction. So our eigenvalue is lambda n is equal to positive a and a sub n squared, a squared, or our a just now we find the value of a is equal to n pi. So our a is equal to n pi because we have squared here, n pi squared. And what is the eigenfunction? Our eigenfunction is this one. Okay, so our eigenfunction is a3 cos n pi y plus b3 sine n pi y multiplied by sine n pi x. Done. Now, superposition theorem, superposition principle, superposition principle. So this is easy. Just put all of them together. Superposition principle is u total equal to u1 plus u case 2 plus u case 3. So this thing here we call superposition, but we only have u3, right? So our u total x comma y. Sometimes in exam they like to play with you the value of the x and y. Sometimes they will put u and x, sometimes u comma t, like that. So you will become confused. But just is one is x, one is y. So they have two x's there. It's the summation of, because this value here is in n, right? So it will be the answer, it will be in the form of summation because n can start from 1 until infinity. So the value of u total is from n equal to 1 to infinity, and then a3 cos, just copy again lah, n pi y, and then sine, okay, because you can multiply this to this and multiply this to this, sine n pi x plus this one and this one, this summation, a bit weird, n equal to 1 to infinity b3 sine n pi y multiply by sine n pi x. So there are two remaining unknown, okay, that we need to solve. This one and this one. Still we need to find the unknown. Okay. But we still have two boundary condition, right? Just now we applied the boundary condition on y-axis only. We still have the other two boundary conditions. Where are they? Where are they? Okay. This one we use. This one not yet. x0, 0, x 100. Okay, boundary condition number 3. I forgot. x0 is equal to 0. x1 equal to 100. Okay. Now we apply boundary condition number 3. So when we apply boundary condition number 3, okay, to this, we need to replace our y with 0. Okay, when y is equal to 0, this one no problem. This one cos 0 is equal to 1. This one sin 0 is equal to 0. So we only have this one already becomes 0, only this part. So our u total at boundary condition of y is equal to 0, and now x will become the variable, so you cannot touch x, is equal to the summation of n equal to 1 until infinity a3, so cos n pi y is equal to 1. This one become 1, and then we have sine n pi x equal to 0. Do you think you are done here, right? But actually no. If you still remember Fourier sine series expansion, okay, try to recall. Okay, this is the net part, so I put other color. Maybe we use black now. So if you can recall, half range Fourier sine series expansion. Okay, you know that this part is very important, very important. Okay, now fx in the Fourier series expansion, right? So fx equal to bn sine nwx. And you can find the value of bn you can find the value of bn is equal to 2 over L from 0 to tau, or L to negative L, and negative L to L, fx sine nwx. Okay, this is, we want to use this for case x0, yeah, dx. Okay, so our fx is equal to 0 because y is equal to 0. Now our fx is equal to, okay, sorry, if fx is equal to 0, okay, and then because of our fx is equal to 0, when we perform integration, we will get nothing. So our a 3 sine, our a3, sorry. So from here, when we compare this, with this, x is 0, this with this, so this is our bn actually. Okay, so our fx is equal to 0, and then our a3 is equal to, okay, when it is equal to this, this thing here, we can find bn using this formula here. So our a3 is 2 over L 0 to tau our fx sine nwx dx equal to 0. Okay, so our u total xy equal to the summation of, because this one is equal to 0, a3 is equal to 0, right? So a3 is 0. Now we only have this part, because this part is already 0. 0 multiplied by all of this, they will get 0. So our new u total is, only we have b3. A bit confusing, but then you can do a lot of exercise, or maybe in your support sheet later, make sure you have one of this example here, so that during the calculation you will not get confused lah. You know what to do next. That's what I mean. So b3, we only have b3 sine and pi y, because we replace, we have y now, sine and pi x. Okay, only we still have the last boundary condition, which is boundary condition number 4, because now you see we only have this one unknown. Our unknown is equal to 1. Just now we have 12, right? Now we reduce it to 12, so we are in the right track. So boundary condition number 4, what is that just now? At x is equal to 1, right? It's equal to 100. Okay, so our u total now is equal to the summation of, because the value of our answer is in n, so we need to put this summation thing, b3 sine n pi, okay, because now our value of y is equal to 1, right? So we need to replace this y 1, so we have n pi now, and then sine n pi x. So this is equal to 100. So our fx is 100. Also, we can compare with this. Okay, when we compare with this, okay, so we recall our fx is equal to the summation from n equal to 1 to infinity bn sine nwx, right? And then our bn, how to find this bn here, is equal to 2 over L 0 to tau, the integration, fx sine nwx dx. Okay, now we notice that this one is actually comparable to this. So our B3 is equal to, so our B3 is, 1 minute. Okay, now we can compare this and this. Sorry. Okay, so this part is this part, and this Bn is this part. So Bn is equal to this. So this and this are equal. So our B3, okay, sine n pi, which is here, is equal to here, 2 over L, 0 to tau, sorry, fx sine nwx dx and then, so we have the value of w, right? So w is equal to pi. W is equal to pi. So n pi x and wx. So our w is equal to pi. So w is equal to pi. Now, what is your period? If you remember, w is equal to 2 pi over p. So our p now is 2 pi over w. Our w is pi. So we have the value of period equal to 2. And then L, you know that L is period divided by 2. Our L is 2 divided by 2 is equal to 1. And our fx is equal to 100. And then finite interval, our tau is 1. Okay, so we can perform the integration. So our B3 equal to 2, and then we have 100 here. Sorry, so this here is 100. Our fx is 100. Yeah, our fx is 100. This is right. So 100 times 2, we have 200. Again, sorry. Okay. B3 sine n pi equal to 2 over 1. Integration from 0 to 1. Our fx is 100. Sine nwx dx. So we get the value of our B3, the coefficient only, 200 sine n pi, integration from 0 to 1, sine nwx dx is equal to, you perform the simple integration here, you will get 200 sine n pi, and then negative cosine n pi. This is when you substitute lah. Okay, n pi, and then you will get 200 n pi. We bring this here. So sine n pi. So the hyperbolic sine n pi. 1 n pi, you know, it's n pi cos n pi. Equal to negative 1 and n, so that your solution will be in term of even and odd number. This is very important, okay, for you to remember. Okay, this is your final answer. We have solved all the unknown and obtained the particular. So this is the particular solution. So this is actually the value of B3 only. Not yet done. So we only have this part, B3 only. So we need to substitute again. What is the B3? And then we have this continuation. So the final answer is our u total of xy is equal to, just now we see that our b3 sine n pi y, sorry, we have the value of b3 here. So our b3 here is, copy again, 200 n pi hyperbolic sine n pi, and then we have 1 minus negative 1 to the power of n, and then copy again this thing, sine n pi y multiply by sine n pi x. Okay, done. This is the final answer. Okay, I will still want to show you other example, but I will continue in the next video. Okay, I hope you try to watch this video a few times before coming to the exam, and then in the next video I will share with you some tips for final exam. Okay, Assalamualaikum, and have a good day. Bye.